Okay. Hi everyone. Myself Soham Banerjee. I am from the Department of Mechanical Engineering at IIST Shibpur. I'm currently pursuing my major in mechanical engineering. I'm currently in my seventh semester. Uh, so, first of all, I would like to thank Sitangshu Sekhar Viswas sir for giving me this opportunity to explain about the project work that we are working on, the leak before break criteria, which is very important, also known as the Griffiths criteria. So, basically, first you have to know what is leak before break criteria. Why do we need to implement it? So, uh, in, if you visit any nuclear plant in nuclear reactors, there are coolant pipes which carries very hot liquid sodium. The temperature of the liquid sodium within the coolant pipe is very high. Again, it has radioactivity. As a result, what happens? Pipe, the coolant pipe, it has to be made of very hard material. Again, due to radioactivity and other reasons like high temperature, it becomes very brittle. So there is always a chance of brittle failure of this material. That is a sudden catastrophic failure that has to be avoided. So there are various reasons for this kind of catastrophic failure, like when all of a sudden, let us say we are closing some valves or we are opening some gate valves, then what can happen? Then there may be some fluctuation of pressure within the pipe, and that pressure uh, may cause some stress to rise within the cracks that are already there, or within the existing cracks that are already there in the pipelines, right? So during the manufacturing there may be some cracks, and there may be some existing cracks, and at the tip of the crack there may be rise in pressure, there may be rise in stress due to this pressure transients. And if this uh, stress goes beyond the uh, ultimate tensile strength, then there may be a sudden catastrophic failure, and that you need to avoid. That's why you need to implement the leak before break criteria, so that before complete failure occurs there would be leak, and you would be able to identify that, and would be able to um, would be able to uh, repair that leak within the time, so that there will not be any catastrophic failure. So today I'm going to explain about the hydraulic transient, how the pressure fluctuation occurs within the pipeline using the Deltates Wonder software. So we are going to take three cases. Uh, uh, okay, okay. Let me check once. Wait. One second. Maybe there is some problem. Uh, okay, let me check. Wait. I need to move this. Okay. Okay, so this is the user interface of Deltates Wanda software, as you can see. Okay, so there are three cases that we are going to talk. In the first case, we are going to take a pipeline setup. Uh, in the first case, what we are going to do, basically, we are going to close the valve within 10 seconds, and then we are going to see how the pressure fluctuation occurs. In the second case, we are going to do it for 30 seconds. The valve closure time would be 30 seconds. And in the third case, what you will do, you will first keep the valve open up to 90 seconds, then you will close it within 10 seconds, then you will keep it open for another 10 seconds, then you will again open it within 10 seconds, and then we will again open it, and then keep it open for another 200 seconds. So first, as you can see, first I have taken a reservoir that is indicated by B1, then I am taking a pipe P1 and another pipe P2. Okay, now let me take a vent in between those two pipes that I am going to connect. Okay, so let me connect this pipe to a standard butterfly valve, and that butterfly valve is going to get connected to the sink, right? B2, that is mentioned by B2. Yeah, so to connect these components, I'm going to click on the connector line tool, and then I'm going to connect the reservoir to the pipe P1. As you can see, then P1 is going to get connected to P2, and P2 to the standard butterfly valve, and from the butterfly valve to the sink, and the vent is going to get connected in between those two pipes. Okay. Okay, so when you click on the element, as you can see on the right side, there is the box where the inputs has to be given and the output are going to be shown in the orange colored box, that is by the message box. So let us first take the height of the 30 meter, the reservoir to be at a height of 30 meter. Okay. Okay, before pipe P1 I should take the connector line. Okay, let us give the same elevation of the connector, because this connector is going to connect the tank or the reservoir to the pipe, so it would also be 30 meter. As you can see, I have modified. Now I am going to click on the pipe, and in the pipe property the cross section would be circle. Let us take the inner diameter to be 200 mm approx. Yeah, and collision mode, water hammering. In the wave speed mode, we are going to change it to the specified wave speed mode. We are going to specify some velocity head, and let us specify the velocity head to be 1400 meter per second. In the roughness, so first we need to understand what is wall roughness. So roughness is basically the irregularities, the asperities on the inner surface of the pipe, which basically contributes to the pressure loss when the water or the liquid flows through the pipe, and it has a contribution to that pressure loss. As per the Darcy-Weisbach equation, you know that pressure loss equal to friction factor times length upon inner diameter times v square by 2g, which is nothing but the velocity, which depends on the specified wave speed that you have already specified. And now I'm going to define the wall roughness, that is basically affects the friction factor. Friction factor depends on the wall roughness. Okay, so it has some asperities. So that asperities, that the average can be taken. So I am going to define it as 1 mm. It has to be quasi steady, and the geometry input, let us take it to be length height, because it is not a horizontal or a vertical pipe. Okay, so now let me define the profile. Click on the profile icon on the right side, there is 3 dots. If I click on it, this table will come, and here I have to give the pipeline A. Let me show it. Okay, it cannot be shown here. Let me open the PPT. Yeah, okay. How the pipeline would be, let me show it. The first pipeline, it would have some kind of profile like this. So it will just the height of the pipe will decrease up to the reference point. The reference line, let me take the reference line again with the help of the ruler. Okay, so this is the reference line, you can see. Okay, now from here again the pipe is going to rise. Okay, let me draw it. Yeah, So let us take, there the tank is connected, and here the pipe is connected to the second pipe, which is the horizontal pipe, and there the vent is, as I am drawing over here, and this is the horizontal pipe, pipe 2, and the pipe 2 is connected to a butterfly bulb. And sorry for my drawing, wait. So let us suppose this one is the butterfly bulb, and then this is going to get connected to the sink or the reservoir or the sink, yeah. Yes. So I have to give pipe 1 this kind of profile, and for that I cannot select length. Length is for vertical or horizontal mainly. So I have to give here length height profile. Yes. So okay, let me open the Delta. Okay, first I should tell something like the first you have, after opening this related window A, you have to select on the model and the mode and option. Then you have to change it from engineering mode to transient mode, because you are going to do the study over a period of 200 seconds. So it's a time dependent study. So you have to first change the mode to transient mode, right? Then as I earlier mentioned, first I am going to take a reservoir. Okay, then the pipes. Yeah, I'm not going to explain it again. Second pipe, and then there is the vent in between those pipes, then there is a standard butterfly valve, and then there is the reservoir. Yes. So using the connector line, I'm going to connect those elements as I mentioned before, like as I connected earlier. Okay, wait. Yes, let me move it a little bit up here. Now let me click on the tank. So first I am going to give the properties of the source of the reservoir, 30 meter, which is at a height of 30 meter, elevation 30 meter. Then of the connector line, it is also going to be 30 meter elevation, as I have explained before. Because it is going to connect the reservoir to the pipe, and it is going to be at the same height as that of the reservoir. Okay, then for the pipe, first let me give the values. The diameter is 200 mm, as I have taken earlier. Next, the specified wave speed, and first let me change it to specified. Yes, and wait. Okay. In the specified wave speed, we are going to take it to be 1400 meter per second. That's an arbitrary value we are taking. And the wall roughness, as I mentioned earlier, we are going to take 1 mm. In the geometry, we are going to take the length height profile, as I mentioned. And now I am going to give the profile with x distance. First I have to give in the table x distance and the corresponding height. Okay, so let us take at x equals to 0, the pipe height is at 30 meter. As we know, the pipe is connected to the reservoir, and at x equal to, let us take the length to be 6 kilometers, like 6 kilometers, yes. And let us take at a distance of 3000 meter or 3 kilometer, the height is 0. It is at the reference, the pipe comes to the reference. And at 6000, it is it goes to an height of let us keep the height to be 5 meter. Yes, Okay, now I'm going to delete the extra row with the help of that option delete row. Yes, and if you want to insert any other row, you can click on that also. Yes. So the accent table has been given, profile table, not accent table, profile table has been given. Now the other things are already there. Now let us click on the character, and the character is going to be at the same height as that of the uh, outer end, like the as the end of the pipe one. So it will be also at height of 5 meters. So that's what we are going to specify at the elevation. That is the input parameter for the connector that we are going to keep. Now let us specify the properties for the vent. Okay, so let us take an elevation offset of it is on the pipe, so I should not take any offset. Let us take it to be 0 meter. Laplace coefficient, it has some range between that you can see. If you just go to the table, you can see the range. Let me give it later. First let me give the ambient air temperature to be 40 degrees Celsius. As you can see, I have already given, and the let me check. Okay, I have given the ambient air temperature 40 degrees Celsius. Vent type has been checked. Let me get the initial air volume to be 0 meter cube, and the residual air volume to be 001 meter cube. Let us take that is the residue air that would be in the vent. And let us take the Laplace coefficient to be okay, vent discharge coefficient. Okay. Let me change the vent. Let me take the vent based on discharge coefficient. It would be better. Okay, we can specify the discharge coefficient, and it would be better to simulate. Let me do it. Okay, so now let me give the properties. As you have mentioned, elevation offset would be 0 because it is connected on the pipe at a height of 5 meter. Initial air volume to be 0 meter cube. Residual air volume, let us give again 0.001 meter cube. Inlet discharge coefficient, let me give the 0.001, yes, or 444, let 4 be, okay, 0.004, and the outlet discharge area to be 0.004 meter square, to be same as that of the inlet discharge area. And the inlet discharge coefficient, let us give it to be 0.7, and the outlet discharge coefficient to be same as that of the inlet discharge coefficient, that is also 0.7. And the ambient temperature 40 degrees Celsius as I have given earlier, and let us take the Laplace coefficient value. We can take an arbitrary value. As you can see, it is recommended that it should be less than 1.4, so let me take 1.4 for it. Okay. Okay, this Laplace coefficient may vary depending upon the type of vents. Okay, now let us specify the properties for pipe P2. Okay, so it will be of circular cross section. Inner diameter will be same as 200 mm. Calculation mode water hammer, and it's to be specified, and I will give it to be 1400 meter per second. Again, the wall roughness would be same as that of the pipe 1 mm, and now because it is a horizontal pipe, so the geometry input mode would be length mode, and I'm going to specify the length over here. So let us take the length to be 6000 meter or 6 kilometers. Now let us specify the connector line. The connector line would be at the same height as that of the pipe, so let us specify to be 5 meter. Now let us select the standard butterfly bulb. Okay, so let us change it to standard. Yes, characteristic type. Then the type would be a butterfly valve. We can change to any other valves we want. So now here we are going to simulate it on standard butterfly valve. In a diameter would be 200 mm, same as that of the pipe, and it would be based on position, and initially it would be fully opened. Okay, now we have to click on the accent table, and there at the right bottom there is an arrow. We have to click on that, and we have to change the option to use. Yes, because we are going to change the position or the opening of the bulb with time. So at initially it was closed. Now after 10 seconds it is going to be initially it was open, sorry, and after 10 seconds it is going to be fully closed, and then it is going to remain in that position. Okay, so at time 0 it is 100% open, and at time 10 seconds let us give it is going to be completely closed. We are gradually closing it, like we have to close it gradually from 0 to 10. So there will be some after closing we are going to keep it closed for up to 200 seconds. So let me put it here in the time column first. Okay, in the next, yes, and in the second, so okay, in the second case, I'm going to close it at 30 seconds. So let me give it for now 10 seconds and 0. Yes, let me at 200 seconds it is going to be remain 0 because it is going to remain closed. Now let me delete the extra row and cut the accent table. And then this connector is also going to be at the same height of 5 meter. And now I'm going to define the head of the sink. Let us give it as a head of 5 meter initially, to have an head of 5 meter because it is at an height of 5 meter. Now let me save this file in the name hydraulic hammering. What I should put, hydraulic transient, yes, hydraulic transient case 1. Yes, let me save it. This is a WDI extension, as you can see. That is the extension for Deltiers Wonder. Okay, so I have saved it successfully. Now I need to change certain things, certain parameters. Now let us go to the first fluid window. Here we are going to select the fluid that we are going to deal with. So here the fluid is the water, as you have can see, and all the properties of the fluid are mentioned over here. All the values of the properties of the fluid water has been mentioned over here. Yes, like you can see the density, bulk modulus, vapor pressure, kinematic viscosity, and also the type, Newtonian type. So the rate of shear stress is proportional to the shear stress is proportional to the rate of shear strain. That is the Newton's law of viscosity, as you know. Now let me change it to the time parameter pseudo, and here I have to give the time step and the simulation time. So these two are very important things that you have to specify. Simulation time would be 200 seconds, and the time step, let us take 0.1 second. Yes, it would be fine. Yeah. Now let us go to the say and calculate transient. We are going to say okay. First we have to save before. Yeah. So first you have to save it again, and then we have to run it. Okay, the study is done. As you can see here, the time has come 200 seconds, 0.0 by 200. Now we are going to check. First click on the valve and we are going to see the outputs here. First we are going to check the valve position, how it varying with time. Okay, so you can see right now, if I click on the valve here, there these message boxes will come where the outputs are shown. Here first I am going to check the valve position. Here clicking on this button, we will plot the graph, how the valve position is varying with time and whether it is as you have specified or not, whether it is just follows what you have specified or not. Okay, so we can see it is following. Next, we can check how the pressure at input is varying, input to the valve. So how it is varying at the input pressure, just click on this. Okay, so as soon as you are closing the valve, the pressure variation or the fluctuation would be there. So that what you are going to check by plotting that. As you can see, after 10 seconds, as you are going to close the valve, there would be pressure rise and then there will be pressure fluctuation throughout the time period, and it would gradually die out after a certain period of time. So as you can see, after 170 or 180 seconds, the intensity has become very low. Yes. There will be fluctuation basically. As soon as we close the valve after 10 seconds, there will be fluctuation, and that fluctuation will die eventually after a greater amount of time, after a certain period of time. Okay. Yeah, there is a fluctuation. There will be fluctuation of pressure, as you can see over here in the graph with time. Now let us check how the fluctuation would be in the pipes, pressure fluctuation in the pipes. So first let me cut it and select this pipe and select this one by pressing Control, and here I can see the pressure is varying. We can check that how the pressure flow is varying with time from 0 to 200 seconds. As soon as we close the butterfly valve, you can see that the pressure fluctuation would be there. So let us plot it first. After selecting it, we can see this blue colored message box. In the pressure, that is the combined pressure, we are going to click on this button, as you can see, and it will plot the pressure profile. Okay. Why? Okay, wait 1 second. Let me check. What happened? Okay, let me let me keep it here, and okay, it has come. You can see the pressure one variation, but yeah, it has come. So okay, so you can see how the pressure profile is varying with distance from 0 to 12,000 meter. So you can see at t goes to 0.00 seconds, how the pressure profile is varying along the pipe from 0 to 1200 seconds. Now we can simulate how the pressure profile is going to vary with time using, first you have to go to the model, then time navigator. So here we are going to get the slider off to the 0 position, and then we are going to play it. So you check on the blue colored line in the way, see how it is varying, so how the pressure fluctuation is occurring after 10 seconds. You can see the pressure fluctuation is there after 10 seconds as soon as we close the butterfly valve, right? It is varying. There is a wave kind of thing, you can see. It is increasing and decreasing like a wave. Yes. So you can see that the pressure fluctuation occurs when we close the valve all on a sudden within a very short period of time due to hydraulic transient. There would be pressure fluctuation within the pipe, and that gives a very high pressure and causes very high stress within the pipe. And even there is even if there is some pre-existing crack, there will be very high stress developed at the tip of the crack. So that is very a fatal thing, a dangerous thing. So that's what we have to simulate beforehand, before designing the whole thing. So you have to check how the pressure is varying with the uh, hydraulic transient. Yes. So you can see here. Okay, so it is done. The whole simulation is done. You can see the phase shift variation. So we are going to do the same thing, and here we are going to close the valve over a period of 30 seconds, from 0 to 30 seconds, and then we are going to keep it closed up to 200 seconds. The simulation time is going to be same. Okay, so that's what we are going to do. Let me cut it. Okay, so I do not have to change anything except the butterfly valve closing, and that we are going to change in the initial accent table, and we are going to click on that table. I am going to modify the table. We are going to change the 10 seconds to 30 seconds because it is going to get closed within a period of 30 seconds. Okay, and other parameters are going to be more or less same. It is going to be same. So let me save it with another name, and this one I am going to save it as case 2. Now let me go to the model. Model options, it would be in the transient only, and the fluid window would be water, as you can see, and the time parameters window is 200 seconds and 0.1 time step. And okay, let me now do the transient study, clicking on calculate transient. So it has started calculating. Yeah, the study is done. So first let us click on the valve, and we can see the output in the blue colored box on the right side, as you can see, and that is the properties that you have given, and that is the result that is shown in the blue colored box. Okay, so first let us check the valve position, how the valve opening is going to change with time. Let us plot it first, whether it will follow what we have given or not. Let us click on this. Okay, again same problem. Okay, let me select on it. What is happening? Okay, okay, let me try once again. It came. It will be of same type. So like it will follow what you have given. It will be closed at 30 seconds, just like the before. Instead of 10, it will be closed at 30 seconds. Okay. Okay, I have already clicked multiple times. Okay, let us check the pressure then. Okay, so that is the output pressure, that is the input pressure. Let us plot the input pressure. Why the problem is occurring? It is not coming. Okay. Okay. Let me refresh. Okay. Okay. Let us first see for the pipes then, as it is, or let me try once. Let me try once for 200 seconds. Let us first let us first go for the pipes then. Okay. 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 Let us first select the first pipe and the second pipe, pressing control. Then we are going to go to the pressure in the output, and then I'm going to click on it. You can see the pressure profile over here. How the pressure profile is varying with the distance along the pipe, with the x distance. And now let us simulate it over the period of time. Click on the model, time navigator. Let us, slide is already up. Let us simulate it. Yes. So you check on the blue colored line. At 30 seconds, it is just going to get a high pressure fluctuation, because at 30 seconds it is going to get closed. So you can see, as soon as it reaches 30 seconds, there is a very high pressure rise due to closure of the valve. And you can see the fluctuation, how it is occurring like wave. Okay, so how the fluctuation is going to occur, how much fluctuation is going to occur, it depends on the closing time of the valve, how sudden we close the valve. You can see the pressure fluctuation over here. I think it is nearly died out. No, again it is rising. You can see, you can check. Again it is rising. So there is a pressure fluctuation within it. Within it there is a very high pressure fluctuation, and it gives a very high rise in pressure. So the pressure does not remain constant. There is a pressure fluctuation. As you can see after the closure of how it is occurring. Okay, it is done. Okay, it is done. Yes. Okay, now let me 1 second try. Okay. You can see the both things are plotted. The pressure ratio earlier, both things were plotted. Let me try once again for only plotting the valve position. Okay, now 3 things are plotted. Okay, like the thing would be same, like there will be pressure fluctuation. It will not be very different from the earlier case. And pressure at the inlet of the valve will also vary just like the previous case. There will be fluctuation after 30 seconds. There will be a very high pressure rise when the valve is going to get closed any other 30 seconds. You can see here also the green colored line, how the valve is getting closed at 30 seconds. So it is following what we have given, right? It is following that. Okay. And you can also see the pressure fluctuation. After 30 seconds, there is a rise in pressure. Then the pressure fluctuation is there. You can see within the pipe there is some pressure fluctuation. Yeah, there is a periodic, not periodic, kind of fluctuation is there. There is a there is a random fluctuating pattern is there, so there is no specific pattern, but there is some fluctuation. uh, yeah, so it is going to occur whenever we are going to close the pipe, and the thing is going to depend on the time of closure, the time it takes, and when it takes very high amount of time, like when you close the thing within a very short period of time, then there will be a very high pressure rise and pressure fluctuation. Now let us do for the third case. In the third case, first let us click on the valve and let us change in the accent table how the is occurring. Here instead of 30 seconds we are going to keep it open for 90 seconds first, so it would be 100. Okay, it is going to be 90 and 100. Then at 100 seconds, within 10 seconds it is going to get closed, and then within the next 10 seconds it is going to remain closed, and then in the next 10 seconds it is again going to get opened, and again after 200 seconds it is going to remain open. Yeah, so now I am going to delete this extra row. Now let us save it. Let us save it. Let us check the model window. Time parameter. Everything is going to remain same, as you can see. Now let us save it first and save it as case 3. Let us go to the model and then calculate transient. Okay, so the study is done. If I click on the butterfly valve, you can see the output in the position. Okay, you can see after 90 seconds it is closed for 10 seconds, then again 10 seconds it remains closed, then again it opens within the next 10 seconds, and then it is going to remain open. So what we have given, the valve position follows that. Yeah, so that you can see over here. So the green color profile here is going to show the valve position, and the red color is the pressure ratio. Yeah. So now let us try whether you can see the input pressure to the valve. Okay. Again. Okay. Let us try to see the pressure, how the pressure fluctuation occurs at the input of the butterfly valve. Again, this kind of problem is occurring. Let me check. And the pressure fluctuation is going to be there. Okay. First, let us check the pressure variation, pressure profile, and how that profile varies along the pipes. So we are going to select. We have selected 2 pipes together, and we are going to press on. We are going to plot the pressure. Okay. This kind of problem never happened before. I think because of the recording it is occurring. Okay. The resource monitor has been ran out, I think. I have to. Okay, let's. If we click on that, you can see that there is a very beautiful pressure profile. Let me do it again. Let me try this again. Okay, I have clicked multiple times. I think that's why so many windows have opened. This is just because of the resource monitor. Let us again try. Okay, I think there is some problem. My memory has been run out. I think that's why it cannot load or process the plot due to resource issue, the memory issue. I think this problem is occurring. Otherwise it will come very easily. Okay, let me close it and reopen. Then we first will input the model again, and then we will again try to see the pressure profile variation. Let me first click on it. Yeah. Okay, it has come over here. Okay, so you can see the. Okay, it has been minimized. Pressure, input pressure. You can see at 9 to 100 second there is a very high pressure rise. Okay, so at 90, so P1 is the pressure here, that is the input to the butterfly, at input to the butterfly valve, and you can see at 90 to 100 second when you close the valve there is a very high pressure rise. Then again we are keeping it closed for 10 seconds, then again we are going to open it. There is a drop in pressure, you can see at the, and this is basically the profile of the pressure with time, the pressure profile with time, and that is at the inlet to the standard butterfly valve. Yes, so that is shown here by red colored line. Now let us go to the pressure variation across the pipe. So let us select the pipe first, and then let us see the pressure profile. What? Again. Okay. Okay. Okay, let me check. Okay. Let us again click and try again, but it's not coming. Okay. Again, it somehow got minimized and it cannot be processed. The plot cannot be shown. Okay. Okay, where is the... Okay, okay, it has come. Okay, you can see. It has come. I think due to memory issues, it cannot process that data. The browsers open, there are two browsers open. You can see that there are two Chromes are open. So, okay, so you can see the pressure profile in the blue color line and how it is varying with the distance along the x-axis. Okay, now we can simulate it. Click model, time navigator. Then let me take the slider to the 0 position, and then okay, then after sliding up, let us play it. And as soon as we play, keep an eye on the blue color line, how the pressure profile is going to vary with time. See, the time is varying with around 90 seconds. You can see when the time reaches around 90 seconds, there will be some pressure fluctuation. The blue color line will fluctuate. Okay. Okay, okay, you can see now the pressure rise is there. You can see how the pressure rise is occurring. Okay, there is a very beautiful pressure rise, but it will, so you can see that it gives a rise to very high pressure after closure. Okay. So you can see that there was a pressure fluctuation as soon as I closed it, but after a certain period of time it got damped somehow because of the opening of the bulb. Like after 10 seconds we again opened it, so basically the fluctuation got damped, and that's why the pressure rise got damped. And you can see where it is important, because of the hydraulic transient, you can see there is a very high pressure fluctuation within the pipe, which can give rise to very high stress, and that can cause different kinds of fatal failure of the pipeline. And if it carries some very hazardous fluid or some very radioactive fluids, then it has to be taken care of, because this kind of failure is very fatal and dangerous. And there is some pipes, and there are a lot of chemical industries where the chemicals are being carried by the pipes, right? So those pipes has to be designed based on this, keeping this hydraulic transient thing in mind, and so that there is, due to pressurized, there is not very high stress concentration developed within the crack, at the crack tips, and within the pipes. Those cracks, those are present at the pipe. And most importantly, in the nuclear reactors, in the secondary coolant line, there can be leakages. So uh, we have to make it in such a way so that the leakage, before the fatal failure, leakage can occur. So thank you for today. Bye. Thank you.